Canada. And our ex-challenger is going to be Dr. Julia J. Chang from Fudan University. A little bit about our speaker. Professor Christian Nijhuis is a professor of hybrid materials and optoelectronics. He obtained his master's degree from Groningen University, followed by a PhD from Twente, where he graduated cum laude from David Leinholt's group. He then moved across the Atlantic to Harvard University, where he joined the group of George Whitehead. And then from there, he was a National Research Foundation of Singapore fellow, and that allowed him to start his group and his independent career at Singapore. Professor Nijhuis is very well known across the world for his work on molecular electronics and plasmonic, and he will be telling us a little bit about that work today. Professor Zhihong Ne is also a professor of soft material and self-organized systems from Fudan University. He started his PhD in Toronto, working with Professor Kumacheva, then moving over to Harvard, where he joined Professor George Whiteside before starting his independent career at Maryland, and then recently moving to Fudan University. Professor Xin Yu started his independent career at McGill University, and then recently moved to Toronto. Professor Xin Yu is known for his work in MEMS and soft robotics and low-cost diagnostics. Our challenger is a recent graduate of Iowa State University, where he pursued a PhD in my group working on soft matter, and then recently moved to Fudan University with Professor Neer, where he's pursuing a postdoc. And with that, I would like to hand over the floor to our speaker today, Professor Chris Nijhuis. Chris?
Okay, now you should be able to see my screen.
Yep.
Yeah. Well, Martin, thanks for the super kind introduction, and it is really nice to see you again via this channel. And also, of course, I would like to thank and acknowledge all the nice work Alice is doing to make this platform completely possible. So it's a great honor to be here today, and yeah, to be able to tell to all of you what we are doing. So as Martin already mentioned, I used to be in Singapore, but last year I moved back to the Netherlands. And I even moved back to the University of Twente, where I did my PhD. So in a way, it is back home for me again. So the group here is, of course, renovations of the laboratories and everything took a little bit longer than expected for obvious reasons. But this is now the group composition as it is. So it's very nice to see that yeah, the group is steadily growing. And every day or every week, new people are joining, like Sarah joined literally 2 weeks ago, Alessandro last week. And yesterday, Niels confirmed that he will also be joining from February onwards. So it's really great. But most of the work I will be presenting today was done in Singapore. And that is the group I left behind in Singapore. Well, this is an old photo, of course. This was taken before COVID times. On the previous slide, you saw individual pictures because it's not allowed here to make group photos for obvious reasons. But this was still before COVID times. Most people have already found new jobs. And I got an email this morning. Many of my students are from China, and they moved back of China, and some of their work will also be highlighted today. Yeah. I also would like to highlight that very recently, just a few weeks ago, we started a new molecule center at the University of Twente. I'm the vice director of this center, and this will be the center will house all efforts that is being done at this university in terms of molecules. So we are a technical university. We have an enormous engineering faculty, one of the biggest academic clean rooms of Europe, but we do also a lot of chemistry, which is now brought together within in the center. Of course, I'm leading one of the programs that is called computing molecules for obvious reasons, and I will tell talk about much more about computing molecules in the next hour. But the center is very broad. It ranges from green molecules to sensing molecules, but also biological applications. Okay, let me now switch gears and start talking about what I wanted to present today. Well, in the title, I promised that we will talk about, that I will introduce new molecules, molecules that work in electronic circuitry, that can do things that is very difficult to do with silicon, or at least it is very expensive in terms of energy to do with silicon, that even can mimic brain-like computational process. And why do we want that? Well, of course, traditional computers, the computers we have right now, are already incredibly good. Transistors are super small, smallest dimensions are now down to 5 nanometers. Still, every year we can pack more and more transistors on our chips. We are already now in the tens of billions per chip. But of course, there are also a few disadvantages to this approach. For instance, one of them is heat. These things become hot, and because of energy issues and some issues, they don't become much faster. So the clock frequency from computers have not really increased in recent times. One of the reasons why current day computers are power hungry is because although the computation is done on the CPU, the information is stored elsewhere. And the results from the computation and the information from the memory has to be retrieved via interconnects. And there are many energy losses in these interconnects. Then, of course, a lot of the calculations is done with transistors, and transistors turn on and off, and everything is done in bits, which are basically a code for 0 and 1s, and that's it. But that is not how our brain works. Our brain works completely differently than our computers, and of course our brains don't run hot. We can do amazing computation. We can compare pictures and immediately see what the differences are in these pictures, while it is very difficult to do with computers. So our brains are very different. Our brains are dynamic. They do the computation very differently, and it is exactly that kind of hardware that is needed to enable new and upcoming technologies. So the way we treat big data, or the way artificial intelligence work, to make that even better and more energy efficient, it would be great if we would have hardware that could mimic the basic function of our brains. And I believe that molecules are a natural choice to do that. And why that is so I will explain a little bit better in the next few slides. But this is a picture that really summarizes the differences between modern computers and our brains, or nature-inspired computing. This was taken from one of the big consortia here in Europe. For instance, our computers are very rigid, but our brains are very plastic. We learn by making certain connections stronger or weaker, while in our computer, when the transistors have been fabricated, they can never be changed anymore. Our computers work with pluses and ones, while our brains, they use switches that can have any value between 0 and 1 as well. Our brains use parallel computing. We have billions of neurons that can work and calculate in parallel, while in our computers, we do everything sequentially. But really importantly is also that in our brain, we compute and we store the information, while in computers, that is done in the processor and in memory banks that are located at a certain distance from each other. So that is really the big difference. So there's many reasons why we want to have systems that can emulate brain-like computation. So why molecules? Well, molecules are naturally dynamic. They are not static. This is a molecular dynamic simulation of a self-assembled monolayer. And you see that molecules vibrate. It's almost, they dance. Of course, natural systems, they can be ordered, but they can also have a little bit of disorder. For instance, here, all the functional groups are located in the top of the monolayer. But when you look at the molecular backbones, Yeah, in this case, these are just alkyl chains. Yeah, there is some degree of freedom here. Yeah, they have a possibility to move. So if you wish, they look a little bit like spaghetti, but this is still not completely disordered because all the groups are definitely located in the top of the cell. Yeah, so there is both order with maybe a certain amount of disorder, but nevertheless, molecular systems, natural systems, they can convert energy, they can store energy, they can compute. Leaves are flexible. Silicon is as hard as glass. It will be very fragile. These systems are power hungry. This is very energy efficient. So there is many ways, I believe, molecules are very complementary to modern day technologies. Molecules are used by nature. So we can also learn a lot from nature, be inspired by nature. And that is basically the reasons why I think molecules are very interesting. Well, why then molecular electronics? Well, here you see a cartoon where you have two electrodes bridged by a molecule. And you see all sorts of conduction pathways indicated here. Well, very nicely, as a chemist, we look at this picture and the location of this atom or the location of this atom, we can precisely control. All we need to do is to synthesize the particular molecule, and we can synthesize any molecule we want as chemists. But the position of the atoms, or the shape of the molecule, or the structure of the molecule, to be a little bit more precise, within the junction really determines the tunneling pathway. And for instance, the tunneling pathway via this side or this side, they may interfere with each other, and this kind of quantum interference phenomena can be exploited in these kind of molecular junctions. So this is something you really can do with molecular junctions. It is very difficult to do that with silicon-based junctions. Of course, molecules are very small, and when you can make things very small, they become automatically very fast. So here is a very nice molecular diode. It has still the record speed. This was a 17 gigahertz diode, but the calculated cutoff frequency was on the order of 0.5 terahertz. So they have the potential to be incredibly fast. Our computers, they are stuck at a couple of gigahertz. But molecules can do many more things. For instance, if you tunnel across a molecule, tunneling charge carriers, especially when you use electrodes like gold or silver, can couple to the optical properties, the optical modes of the junctions, and excite plasmons and emit photons that you can use with in combination with sensing, for instance. And that is something that is widely studied or in detail studied in a group of Jeremy Baumberg, and now also here at the University of Twente, because Femi Oyambati joined the university as a tenure track position as an assistant professor about the same time as I joined, and he came from Jeremy's Baumberg group, and he will be studying these kinds of optically active molecular junctions. Yeah, and we have also studied in the past quite a bit of these optically active molecular junctions, and I will in a few slides show a little bit more what we have been doing in that area. Yeah, and that is just to highlight what you can do more with molecular junctions. And especially particularly this example I enjoy a lot, because Ismail Diaz-Perez, he showed a couple of years ago that in junctions, when you apply a voltage of, let's say, 1 volt between the two electrodes, the molecule is maybe only 1 nanometer long. So that means you have an electric field of a gigavolt per meter that is really truly enormous. Such high fields really enable new physics, but also new chemistry. And he showed that you can even drive a Diels-Alder reaction electrostatically. Yeah, so this is a really new way to catalyze reactions. So that means in these kind of junctions, you can couple current or tunneling currents to also chemical reactions. And you will see more about that a little bit later, how we can use that to create new kinds of molecular devices, molecular switches that can mimic brain-like computation. So that is what basically I wanted to talk about. We want to have something nature can do. Our brains can compute via completely different rules than our current computers, via a very different hardware where everything is massively parallelized. But here is a zoom in of one of the synapses. Yeah, and basically what the synapse does is, in our brains, we don't have currents, but we have action potentials. And the action potentials propagate along the neurons, but they have to jump or to go across a synaptic cleft. And of course, that is done with neurotransmitters. So the action potential, they can go quite fast, but of course, the transport from neurotransmitters from one side of the cleft to the other, that is diffusion limited. So what is happening is that you have here different processes with different time constants that are coupled together. So fast processes are coupled to slow processes. And that means depending on how many of these action potentials arrive here, how fast is all important in how many neuron transmitters are being released and detected at the other side. And that determines then how the information is transmitted, either with higher intensity or lower intensity, not just 0 and 1, it can be all values. So basically a synapse is nothing else than an analog switch, but the switching depends on the history, and it can have any value between 0 and 1. So we would like to have such a system, such a switch, of which the switching probability, the switching dynamics depend on the past of the device. So that is what we want to create artificially. Well, such artificial synapses do already exist. For instance, Yuri van der Burgt, who is also here in the Netherlands at the University of Eindhoven, he developed some kind of electrochemical cells where current flow is coupled to ion diffusion. Yeah, so then you have also a fast current process coupled to a slower ion diffusion process. Yeah, and they can get excellent properties. So they can really mimic the dynamical features of brain-inspired computing schemes very nicely. And you see here a zoom in that they can access many states. I think here, instead of only 0 and 1s, they can access more than hundreds of states. Here you see another example where current flow is coupled to the formation of filaments. So you see here a beautiful TEM image where filament formation and dissolution is being visualized. Yeah, and then in the current voltage characteristics, you see when you start to apply a voltage, currents start to flow, but at a certain threshold voltage, a filament forms and the current jumps up. But then when you reduce the voltage, you have to go to much lower voltage to dissolve the filament again. And then the current path via the filament is broken and you end up with the low conducting state again. And this kind of hysteric behavior, yeah, that is really what is also desirable for computation, bio-inspired computational approaches. Yeah, and there are many more of these kind of schemes. So you can have also current flow coupled to ionic flow, etc., etc. But all these systems are mesoscale. So it's difficult to see how you can scale them to molecular length scales or atomistic length scales, because filaments need to grow in a medium. That medium can be a polymer, or at least it has to be something. Ions can also only diffuse in a medium. It has to be an electrolyte or an ion gel. There has to be a medium. So these systems are macro scale or mesoscale. But what we want to develop are molecular scale systems that can mimic synaptic behavior, for instance. So that is what we want to do in our molecular junctions. So I would quickly define molecular junctions, because there are two classes of molecular junctions. Many of you are likely familiar with single molecule junctions, where you have one electrode and another electrode that is bridged by only one molecule. And here you see a typical junction configuration where the top electrode is a tip of a microscope, such as an atomic force microscope or a scanning tunneling microscope. But you can also make break junctions like this, where you have two electrodes, and when you bend the wafer, a small neck will snap, and then you can trap a molecule there. Well, as a chemist, we know if we deposit molecules from solution, yeah, there will be many molecules, of course. But if you choose the conditions correctly, there will be only one molecule that is connected to both electrodes, and that's where all the current flows through. The nice things about these kind of single molecule junctions is that it can be very well modeled with sometimes even very simple physics, such as just a Landauer formula. So you can have a very good microscopic description of how these junctions work. But the problem with these junctions is you really can't measure how the molecule sits in the junction. And sometimes it is even difficult to determine whether it's only one molecule, for instance. So you need to do a lot of statistics to figure that out. And also the device to the device variation can be fairly large. Yeah, and often they also work only at very low temperatures. So that is not really advantageous. But there is another class of molecular junctions where the electrodes are separated by a monolayer of molecules. And of course, this junction is still molecular because in this direction, the thickness is only one molecule. So that means the mechanisms of charge transport is still dominated by tunneling. But these junctions can be produced on very large scales, can be very stable, can be fabricated with very high yields. And in fact, the first commercial molecular junctions that are based on monolayers are available. So you can place an order online and you can actually buy them, at least some specific types. Yeah, but then here, often in these kind of large scale junctions, they can be operated at room temperature, where we can also look at incoherent processes, or maybe when you have redox active groups here, you can also think of it as redox processes. Of course, you don't have an electrolyte here. This is all solid state, so it's not exactly the same as electrochemistry. But still, often the redox processes can be modeled with Marcus theory. And of course, once you do redox processes, and then you can also think of chemical reactions and catalysis, of which we just have seen a few examples, right? But in molecular junctions, you maybe also have a combination. It's all in a solid state, meaning there is not really an electrolyte. The molecules are connected to two electrodes instead. So the whole environment is different. So then you can ask yourself, what happens when a molecule formally oxidizes and reduces inside junctions? Well, these are just the Marcus parabola. They basically indicate when charges go from a donor to an acceptor, they have to cross an energy barrier that is always given by a certain activation energy. But if I make the reaction more exergenic, so I give the system more energy, so I lower this parabola, yeah, at some point, this parabola will intersect the parabola of the donor at the minimum, and then you can have charge transfer without an energy barrier. And of course, that is very desirable because that would mean that the current, the charge transfer rate is at its maximum, and you don't have to pay an energy penalty for the activation energy. But Marcus predicted that even if you lower this parabola more, the reaction should become slower again, because this time you would get again an activation energy. And this was called the Marcus inverted region. Well, he predicted it in the 1950s, but it was very difficult to access this regime experimentally, because if you have a donor and an electron acceptor in solution, at some point the reaction rate is diffusion limited. And then you get stuck somewhere here rather than here. So then you cannot prove that you have the inverted Marcus region. And it wasn't until chemists made molecules where the donor and the acceptor moiety are coupled within one molecule via a bridge, a so-called donor bridge acceptor compound, that experimentally the inverted Marcus region could be determined. What Abraham Nitzan predicted, well, in molecular junctions, you should also be able to access the Marcus inverted region, because the molecules are fixed on the electrodes, so we don't have diffusion problems. But then in the inverted region, the energy penalty from the activation energy can be paid by the energy from the electrodes. So that means first we would develop an activation energy. So as soon as hopping becomes possible, then the activation energy should decrease again when you apply more voltage and the parabola start to intersect the minimum here. But then in the inverted region, the activation energy should remain zero. Well, and one of my former students, Yuan Li, who is now at Tsinghua University, well, he demonstrated this experimentally with this donor and acceptor compound. So this molecule was studied both in single molecule junctions in collaboration with Enrique Del Barco, but also in our last area junctions. Yeah, and here you see the result that indeed the activation energy first increased and then decreased again. Well, you could argue the error bars are very large. This effect is very small. Yeah, but nevertheless, it was very important. But since then, we found the same effect in a different molecule, but then much larger. So this also shows that already in molecular junctions, you can do things that is very difficult to do with traditional systems, and you can make your devices more efficient. For instance, here, this molecule happened to be a very good molecular diode where the current in forward bias is much higher than in reverse bias. But at positive voltage, this molecule operated in a Marcus inverted region, so it did not depend on temperature. At reverse bias, the hopping was in the Marcus region, so it did depend on temperature, meaning by lowering the temperature, we could increase the efficiency of this diode by a factor of 30. So this shows that we started with something very fundamental, but then when you can do it, you can really make devices better. Another take-home message is that we can really do redox chemistry in these kind of junctions. So the charges can be really stabilized on the molecules, and with that we can do something. And that then, of course, brings me to the next part of this talk. Well, let me skip this slide because I think I already introduced junctions and their advantages. I just would like to highlight that you see often very beautiful cartoons of idealistic junctions almost. Really beautiful. But of course, as a chemist, we know we have electrodes in the, we have roughness in the electrodes. And when you are familiar with monolayers, you know that in some phase domains, the monolayers are tilted in this direction. In some phase domains, they are tilted in that direction. So no matter what you do, you always are going to have some defects. But the field has improved tremendously over the last couple of decades. Now it is really possible to minimize the number of defects. And we understand as a community very well how defects affect the junction properties. So also in the junctions that I'm presenting in this talk, we essentially have taken care of all of this very well. So if you want to find more about it, I can recommend this very nice review. But that is very nicely summarized. So what do we want? We want to have molecules that can emulate synaptic behavior. What do we have? Chemists have already made molecular switches for many, many decades. Here you just see a few very well known of them. And they share all one common thing. They switch between only two states, let's say on and off. And that's it. So for instance, here a molecular switch was used to control spin currents. These isobenzene switches are used in many kinds of materials, but they all share one thing. They turn between on and off states, and those on and off states never change. So it's independent of the history. But what do we want? We want to have switches that evolve continuously, where the switching probabilities depend on the history of the device. So they basically remember their history. And many of these molecular switches, they work very well in solution, but it is very difficult to get them to work in a solid state. So a few switches, after a lot of effort, they do work, for instance, in monolayers. But what we want the switches to be working in junctions. So with a top electrode on top, and they should modulate the current that flows across the junction, and they should switch as a function of voltage. So we have actually quite a lot of requirements. So how are we going to make these switches? How do we develop these switches? Well, we have to fulfill quite a few requirements, because here you see an example of a switch from the group of Guo that was published in Science a couple of years ago. Yeah, and this is one molecule that can be switched in single molecule junctions with graphene electrodes. Yeah, and that turned out to be a very stable switch in terms of these junctions, I believe, were stable for years. But you can see that there is stochastic behavior. It is not always easy to predict whether the switch will turn on here or here. So you need to stabilize the intermediate states. Well, the group of Ryan Kiecki is also a former member of the Whitesides group. Yeah, he solved this problem by having also a switch where he could stabilize the on and off states via a protonation reaction. But he did it in such a way that he removed the top electrode, exposed the switch to a solution that had either the protons or not, and then reintroduced the top electrode again. So he could definitely stabilize the charges. But yeah, of course, we would ideally do this all in situ without having to remove or add the top electrode. So how are we going to do that? So here are two examples of switches we have developed recently. So this is a dual functional switch where we have a diode functionality in series with the electrostatic on and off switch. And here we have a molecular switch, which is also a diode functionality in series with a memory element. Well, in the next few slides, I will go in much more detail about how these switches work. But let me quickly introduce how we make our junctions. So we make them using the Eain technique. Eain stands for a eutectic alloy of gallium and indium. It's a liquid metal, it's non-Newtonian, so you can shape it, and that is because at the surface there is a very thin layer of gallium oxide. That protects the metal also from alloying with the bottom electrode. It stabilizes the liquid, but it also makes it to shape it. Yeah, then we can make these tips, and we just lower the tip and bring them in contact with the surface. And then they will just yield and form a good contact with the surface rather than destroying the molecules. Well, we can also stabilize this liquid metal in microfluidic channels, for instance, and then we can make a whole array of these junctions, so we can also upscale it. So this is a very versatile tool. Yeah, and now many groups in the world are using this method to form junctions. And yeah, this method is compatible with all sorts of different types of molecules with different reactivities, but also biomolecules, including proteins and DNA molecules, but also nanoparticles. So it's a very good method to form electrical contacts, yeah, to soft materials. And to a broader extent, this material is now used in an enormous amount of different areas of research, including healthcare. Yeah, and Michael Dickey, also former Whitesides member, he does really fun stuff with this. He has a beautiful video on YouTube where he basically uses this material to emulate the Terminator. You should look it up. It's really fun to watch, but he also uses it for 3D printing. Yeah, and Martin Thuo, he also uses it for nano welding and micro welding applications. So it's really beautiful what you can do with this material, but we make molecular junctions with it. So how do we develop these switches? What do we need? Well, this is now an energy level diagram of the junctions. Here in yellow is the Fermi level of one of the electrodes indicated. And that is the energy where the electrons in the metal can move freely. And this is the Fermi level of the other electrode. And then in between, of course, we have the molecule. Well, the molecule will have a molecular orbital that is, in this case, I drew here the HOMO. Yeah, that is maybe lower in energy than the Fermi levels. In case a LUMO is closer, then it will be maybe above. It doesn't really matter. for this example, so I just choose here a HOMO. And of course, this molecule will have a certain interaction with the electrodes. And that gives you two parameters: the energy offset between the molecular conductive orbital and the Fermi level. That basically determines the tunneling barrier height, and how strongly the molecules interact will also determine what the tunneling rate is going to be. So you have two parameters to control the current, and that is by changing the tunneling barrier height or the molecule electrode coupling strength. So if you have a molecule, a molecular switch that changes the barrier height or the coupling strength, then you can change the current. That's it. That is all we need. We just need to have a molecule that changes the tunneling barrier height or the coupling strength, and then we already have a switch. So we don't need to have conformational changes like azobenzene switches. We don't need to have anything rotating like the Ben-Feringa motor. We just need to have a molecule that changes the tunneling barrier height and the coupling strength. And that's it. And then we can already make molecular switches. Well, to create memory, we also need to stabilize the on and off states. And that is difficult to do because of the high fields we have. But as Ryan Kiyaki has shown, by coupling charge injection to chemical reactions, in principle, you can do that. So let's see how that works for these two switches I briefly highlighted before. So here we have methyl viologen, which is very well known. If you reduce it, you create a radical cation that readily dimerizes. So here charge injection is coupled to a dimerization reaction. And here you have two counter ions. Here you need only one. So one of the ions will also move to one of the electrodes. And because of this charge separation, we can stabilize this state. Well, with these ferrocene junctions, yeah, it turns out that the ferrocenes, you can inject charge in the HOMO at the voltage where the top electrode is negative. So then these ferrocenes are positively charged. This is negatively charged. So here we have an electrostatic interaction. So here we will change the molecule electrode coupling. Here, the energy or the tunneling barrier height for this monomer will be very different than for this dimer. So here we change the tunneling barrier height, and here we change the molecule electrode coupling. So let's see how that works out. And of course, both molecules are asymmetrical. We have an insulating alkyl chain here and a conductive molecular unit here, and that causes the diode functionality. Yeah, so that explains both functionalities. So why do we want to have dual functional molecules? Well, in this example, we have a diode functionality in series with a variable resistor. Well, that is called a 1D from diode, 1R from resistor, random access memory device. So this is an example from the group of Takili, where he created with organic polymers a memory function. So one junction, so one electrode, organic layer electrode junction to create the memory functionality. But he added a couple of more layers to create a diode functionality. So you get a multi-layered structure. And in other commercial devices, even the number of layers can be 8 or 9 or 10. But the problem is, if I now apply a voltage across all these layers, the voltage will drop across each of those layers. So for some devices, you need to bias them with 10 volts. So the drive voltages are enormous to get proper switching. Yeah, and of course, that is very power hungry. These layers can be tens of nanometers thick. So the total thickness of the entire device can be even more than 100 nanometers. So that is becoming too thick. So this is not small anymore. But nevertheless, such devices work very beautifully because you see here the current is much higher than here. So you have a beautiful diode functionality, and you see a big hysteresis here. So you have a beautiful memory functionality. Yeah, and then the advantages of having a diode functionality in series with this memory functionality. Well, if you have such a crossbar array functionality with the memory elements everywhere, Well, if let's say this memory element is shorting, is not working very well, when you don't have a diode, you can have sneak path currents, which causes information loss. But when you have diodes here, you always block the possibility for these kind of sneak path currents, right? So that is the advantage of having two of these functionalities. Well, if you can create this within one single molecular monolayer, yeah, then you can imagine that the drive voltage can be reduced dramatically, because now you have only one layer where the voltage will drop. Well, and that works very nicely for these molecular switches here. So this molecule is only 2 nanometer thick, only 2 nanometer. We see that the current here, it's much lower than the current there. So we see a beautiful diode functionality. Yeah, and we see very nicely that here the molecules switch on, the dimerization. And here we see another switching event, and that is what we relate to ion migration. Yeah, and then when you reduce the voltage again, you get massive hysteresis. Yeah, and all within 1 volt. So this is a beautiful molecular switch where we have two functionalities present in a layer that is only 1 molecule thick. And you see here a DFT calculation of the dimer, and you see beautifully that the HOMO and is completely delocalized over both molecular units. So you can imagine that the HOMO-LUMO gap of the dimer is much smaller than the HOMO-LUMO gap of the monomer. That's why when the device turned on, the current increased, because we reduced the tunneling barrier so much. Well, by having now tunneling coupled by dimerization and ion migration, we could create this beautiful dual functional switch. Yeah, and does it really result in non-volatile memory? And the answer is yes. Here you see that we could switch between the on and off states about 80 times, and the on or off state could be retained for 1 hour. So this dimerization with ion migration did indeed stabilize the on and off states in the junctions, despite the fact that we apply electric fields of the order of a gigavolt per meter. Yeah, so this really worked wonderfully. Well, these devices we have characterized in detail, and we found that a counter ion is very important. So when we use fluorine instead of iodine, device properties really diminished. Yeah, and that of course reinforces the proposed mechanism where the ion migration is responsible for the stabilization of the on and off states. Yeah, and here we prove that we have indeed dimerization in these monolayers, but yeah, let me go quickly over it, because I see that I'm already talking for 40 minutes. But we did characterize all of this in detail. And as I already mentioned in the introduction, the advantage of using monolayer devices is that the monolayers can always be characterized, also with spectroscopy. So for instance, with NEXEVs, we can determine the energy of the LUMO with respect to the Fermi level, and with UPS measurements, we can determine the energy of the HOMO with respect to the Fermi levels. So we can basically experimentally determine the tunneling barrier height or the whole energy level alignment of the system. Well, then in conjunction with DFT calculations and so on, we really could summarize the operating mechanism essentially in this energy level diagram, where because of the dimerization, we really reduced the HOMO-LUMO gap. And in this case, the energy of the HOMO increased a lot because the LUMO was pinned to the top electrode. Yeah, so here we had a switch by changing the tunneling barrier height, where the on and off states were stabilized by ion migration, dimerization coupled to ion migration. So now let's go back to this other switch here, where we have a diode functionality in combination with an electrostatic on and off switch, where the molecule changes in the interactions with the top electrode. Here we see no hysteresis, because here we don't really have a stabilization of the on and off state. Yeah, but my student, former student, he's now at Minan Normal University, Xiaoping, really found that these molecules gave a tremendous rectification ratio of nearly 1 million. But then my good friend Enrico Del Barco, he tried to model it with the Landauer equation, and he said, well, Chris, we have a problem because the maximum current that can flow through a molecular orbital is limited by the quantum resistance. Yeah, so that means the maximum possible rectification is about 1,000, but you have much higher rectification ratios. So how is that possible? So the only thing we could think of is we need more molecular levels. But yeah, the number of molecular levels for a given molecule is of course fixed. So that means the number of molecules in the junctions must change. Well, how does this now connect to this electrostatic on and off switch in series? Well, for that, we need to look at the optical properties of junctions. So I already mentioned in the introduction quickly, if you have tunneling charge carriers, the way I see it, when a tunneling electron ends up in the Fermi sea, so to say, to speak very freely, a very simplistic picture, you can imagine that it will push away the surrounding electrons for electrostatic reasons. So you cause ripples or waves of these electrons. And that is exactly what a surface plasmon polariton is. That is collective oscillations of electrons at the metal dielectric interface. Yeah, and okay, this movie doesn't play, but it's not a big deal. That was just a movie to show, yeah, that indeed metal surfaces or called nanorods can support these plasmon modes. So that means in our tunnel junctions, because especially when we use gold electrodes, we always excite plasmons. And of course, the plasmons will only excite it in the part of the junctions where the current flow. So already quite a few years ago, I wrote a grant to study light emission from these junctions. The plasmons can decay in photons, so they should emit light. And Tao Wang and Dewey, they really were the two in the group who did set up this microscope system. And this was one of the very first measurements they did. So now we look through the back electrode, through the bottom electrode. We typically use 20 nanometer thick silver or gold so we can look through it. We apply a voltage, current flows, and we see light emission. And you see very nicely that the light comes from discrete spots. Yeah, and that of course tells you that you have a rough electrode. Yeah, and of course that makes sense because we just make an Eain tip, which we then put on the surface. So it would be very unlikely to have a very smooth contact. In fact, we have a very rough contact. Yeah, and we know already from scanning tunneling microscopy, for instance, that the tunneling current is very sensitive to the distance. So only in certain locations where the distance between the top electrode and the bottom electrode is the smallest, yeah, that's where the current will flow. So we see beautifully that we have these nice emission spots. And even more beautiful is that they blink. Yeah, and of course, when you see something like that, you think I'm looking at single molecule events because it is very difficult to imagine that 10 or 100 molecules would go on and off simultaneously. So do we really look at single molecule events? Well, we did some statistics on it, and the blinking statistics are very similar to those obtained from quantum dots or single molecule emitters. So we have many reasons to believe that each spots represent conduction through a single molecule. In other words, we can count the number of molecules that conduct current in our junctions. So when we now do this for the ferrocene junctions, where we have the electrostatic on and off switch, we can just simply count the number of spots as a function of voltage. And then you see that the number of spots increases exponentially with the applied voltage. So that really means there is a drive force. That really means that the number of conducting molecules increase with the applied voltage. When we remove the ferrocene moiety, so we don't have oxidation of ferrocene going on anymore. So we remove the electrostatic switch from the molecule. Yeah, and we just use a normal alkanothiol. And then we just see a linear dependency because maybe some spots at low voltage were too dim to be seen at high voltage. Yeah, so we just see a linear increase, but that means there is no drive force. Of course, I showed these results to a very good friend of mine, Damien Thompson. And I asked him, can you model this? Because for me, this is a little bit difficult to understand. What could be the drive force? Is it really an electrostatic interaction between the oxidized ferrocene units and the top electrode? Yeah, and then he sent me back this result. He just showed the monolayer, no top electrode. And when he puts the charge on the molecules, yeah, the monolayers swell. And then I said, how does this work? And then Damien had to laugh, and he just sent me back in an email this picture. And then, of course, everything became clear. Already electrostatic repulsion between the molecules is already enough to force more molecules to form a better contact with the top electrodes. That's it. So when we then use the counting molecule measurements results, and we corrected the formula, the Landauer formula, by simply adding a functional where the number of molecules are allowed to vary as a function of voltage. Here are the measurements. The blue line is what we used in the fitting. Yeah, we obtained a very nice fit. Yeah, but of course, then this convincingly shows that we have a molecular diode in series with electrostatic on and off switch. So again, this is a beautiful example where molecules can switch currents in junctions, but they're not per se the type of switches chemists would have thought of, because they always think of conformational changes, structural changes, but we just need molecules that change either the molecule electrode coupling strength or the energy, the tunneling energy barrier heights. And Nicolas Clément and Akira Fujiwara, they wrote this very nice news and views in the same issue our paper was published in, calling it a breaking of the Landauer limit, which is of course very beautiful if you put it like that. But of course, we did not break the limit. We did not break the Landauer rule. We just found a very nice way to bypass it by having this kind of switching phenomena. So summarized in the energy level diagram, then this looks as follows. In this particular switch, we did not change the energy barrier height per se, but we did change the molecule electrode coupling strength. So now we can do all this. So in the design of our molecular switches, we can change the energy level alignment, we can change the molecule electrode coupling strength, we can stabilize states in high fields. How do we create now switches that are dynamic, that change the switching probabilities dynamically? Because the switches I have shown to you, they did not do that. They cannot mimic synaptic behavior. So in the last 10 minutes, I will introduce the next system that has these properties. So one of my students, Yulong Wang, he synthesized this beautiful molecule. He just submitted his thesis, so hopefully soon he can defend. He synthesized this beautiful molecule that is called HATNA, that has 6 of these nitrogen centers. Each of these nitrogen centers can be reduced. And when you reduce it, a proton will be added and you form a new nitrogen hydrogen bond. So you form a new NH bond. And of course, this is beautiful because this redox state and this redox state, this new redox state, is then stabilized by this new covalent bonds. So this should be very stable. Of course, when you add an electron, you charge the molecule, but then by adding a proton, you neutralize the molecule again. And that is exactly how biology also moves electrons in our bodies, for instance, using NAD, NADH, for instance. So this is called electron transfer coupled to proton coupling step, or ET-PC, often written in papers. But in our case, the proton source, the protons come from water and air. That's it. So we have fast current flow that can be described by tunneling equations. coupled to very slow diffusion of protons. So now we fulfill the requirements that we have two processes with different time constants coupled together. Yeah, and when we have, for instance, this reduction state, and we have this reduction state, how fast we go there really depends on proton diffusion. So if we change the voltage very quickly, yeah, the proton diffusion cannot keep up. And we maybe need many cycles to go from this state to this state. Yeah, so that is where the delay comes from. And that is exactly what we need to mimic synaptic behavior, where, for instance, action potentials are coupled to slow diffusion of neurotransmitters. Yeah, so this is really an analogy to a synapse. We have fast current flow. Here we have fast action potential flow that is coupled to diffusion of protons from water. And here the information is coupled to diffusion of neurotransmitters. Yeah. So does this switch really work? So here you see basically what is happening. So electrochemically speaking, you can detect these four states. So here you see a typical cyclic photomegram of these monolayers, and you can see very beautifully these four states. Well, it's all scan rate dependent. So if you change the electrochemical conditions, you can actually see more states. But with density functional theory calculations, you can also calculate the projected density of states for each of the different molecular states. And I would like to point out, we have 6 electron addition steps, but also 6 proton addition steps. So we have plus 0, 13 different states. So Damien Thompson calculated all of these states, but only a few are highlighted here. And we see for the molecule in this state, we have a very large homo-lumo gap. So we could define this as an off state. Tunneling here will be slow. But for some of the intermediate reduced states, we see a new intergap state right in the middle of the homo-lumo gap. So tunneling across here will be extremely fast. So this will be an on state. But then for the fully reduced molecule, this intergap state disappears again, and we end up with a molecule that has a very high homo-lumo gap. So it will be turned off again. So this is a very interesting switch because we can turn it off, on, and off again, and then we can reset it and start the whole process again. So this is a very dynamical thing. But I also said with increasing voltage, we can access the different state. Here the molecule is off. Here the molecule will turn on, so the current will increase. Here the molecule will turn off again, so the current will decrease. And that is exactly what we see in our current voltage measurements. The molecule is off, so we see that the current is only slowly increasing, but then the molecule turns on and the current increases rapidly. Then the switch turns off again and the current decreases. Well, this is very interesting already on its own, because now the current decreases despite the fact we apply more voltage, and that is very unusual. Normally the current always increases when you have normal tunneling barriers or when you have normal resistors. But in this case, we see this so-called negative differential resistance. But we need to go to positive voltage again to oxidize the molecule back to its original state. And that's why we get massive hysteresis. So this means that all these covalent bonds really do stabilize the different states. Yeah, but now we have a molecule that has 3 functionalities. Here the current is much higher than here, so it's a molecular diode again. We have hysteresis, so we have a memory functionality, and we have NDR. So this is a molecule that has now 3 switching functionalities. Yeah, and that is also quite unique, I would say. Well, just a quick slide to show that with combination of Landauer theory and Marcus-Rate equations, we can describe our system completely. When you have systems with filaments and so on, those kind of artificial neuromorphic devices are always modeled in equivalent circuits. But when you have an equivalent circuit, it doesn't give you any molecular information. Here we have all the molecular information. We have the tunneling barrier heights, so that includes the homo-lumo information. We have reorganization energies, we have activation energies, which as a chemist, you can change by altering. the molecular structure. Yeah, and this is, for instance, tunneling through the on and off states, which is modeled by this parameter chi. But this parameter chi is exactly this energy difference between the LUMO and the intergap state. So even those parameters we could get from our experiments. Yeah, and this really works because now we can define regions where we can do neuromorphic or synaptic behavior. So one of the hallmarks of synaptic behavior is when you mimic action potentials, which are basically voltage pulses, that when you have two voltage pulses that would go across the synaptic gap, depending on the first pulse, the second pulse will have a stronger or weaker signal. Well, in our case, when we have here the first pulse, in this particular example, the second pulse was weaker. So this is called pulsed pair depression. We also have examples where the second pulse is higher. That would be pulsed pair facilitation. So that already tells you this is not an on and off switch, because if it would be an on and off switch, both pulses would have the equal height, the same current. So this already shows that the system works. Well, here you can see it more clearly. Here we have a whole series of pulses with a low frequency, and you see that the voltage pulses are always the same, but the current keeps on increasing. And by only changing the frequency of the pulses, we can also make the current decrease again. Yeah, and that is also one of the hallmark experiments to do if you want to demonstrate synaptic behavior. And this is called spike rate dependent plasticity. Also interesting, you see that this is not a linear decrease, it levels off. Yeah, and that is called habituation. And our synapses do exactly the same thing to avoid overstimulation. So we get that as well. These are the experiments. In red are the modeled data. So our model really replicates this behavior fantastically. But here you see the switching probabilities. They completely depend on the history. This switching probability depends on the history of all these pulses. Yeah, and all these pulses here on this side, yeah, it depends on the switching history of the entire pulse sequence. Yeah, so this really beautifully shows that these are not normal on and off switches, but that they can mimic synaptic behavior. Well, can we then also demonstrate that these molecules are then suitable for demonstrating learning? Well, let's not do the very famous Pavlov experiment, where Pavlov demonstrated if you present dog, the actual animal, a dog, with some food, yeah, it will of course start to create saliva because it sees the food, you know, and wants to eat it. But of course, when you have an entree dog and when you hear the ringing sound of a bell, yeah, you don't start to create saliva because, yeah, you don't associate the bell with food. But then what Pavlov did, he was presenting, every time he was presenting the dog food, he also rang a bell. And then eventually, when he only rang the bell, the dog associated the bell with food and started to produce saliva. So we can also do this with our molecular junctions. And you see here a very simple circuit where we just placed a normal resistor in series with our junction. Yeah, and of course, when we play the sequence that is an analogy of the dog sees food, of course, we get a response from the system. But when we only play the bell, we get basically no response from the system. These are just capacitive currents. When we play both simultaneously, so we train our junction, of course we get a response. But then when we only play the hearing bell sequence, we do get a significant response from our junction. So these molecules have now learned to associate. Yeah, and I see that my time is basically up. I'm already 1 hour talking, so this is basically my last slide I wanted to share with you. When you have new molecular hardware that can do new things, you can also emulate, in this case, logic gates via new rules. Depending on the duration of the pulse and the height of the pulse, we can change the current output. Yeah, and of course, high current or low current, we can define as 1 or a 0. But in this case, we only need one pulse with a certain height or duration to get a 1 or 0 response. So this is very different input than a transistor, because basically we make now use of both the time domain and voltage dependent plasticity of our junctions to emulate logic gates. Well, here you can see the pulse sequences and the response along with the truth tables. Yeah, and we were able to emulate all basic logic gates with these junctions. Yeah, so that really shows you that with new molecular hardware, you can really create brain-inspired, nature-inspired computational processes. Yeah, and of course, I have already shown examples where we were able to reduce energy consumption, or within molecular monolayers of just 2 nanometers. And we have demonstrated how they can be used, potentially be used in new and upcoming paradigms. So a few of the challenges we are now working on is we want to get these molecules to work in large area junctions. So we are now redesigning our molecules to make them stronger, so we can fabricate these junctions with clean room compatible methods. So we want to get rid of the liquid metal, for instance, so we can really make devices that are useful. Well, our devices are still fairly slow, so we want to speed them up by making them smaller. So we're also working on that. Yeah, and then of course, once we have arrays, the next step would be to demonstrate artificial neural networks. And then not only have voltage as an input, but also combine it with optical inputs. So there is also a lot of activity going on in photonics, and recently there have been impressive demonstrations of photonic neuromorphic circuits. So it would be very nice to combine it all together. So I would like to thank you, all of you, for listening for so long to me. And I'm looking forward to answering your questions, and also, of course, to the panel discussion. Once again, thank you very much for all of your attention.
Thank you, Professor Nijhuis. We really appreciate the great talk. And we do have a few questions that if you will be so kind to answer, we would really appreciate it. Thank you very much. It's exciting work, the progress in using molecules to make the future of computing much more energy efficient and more diverse in terms of mechanism.
Yeah, of course.
One of the first questions that came in, one of the questions that came in very early was, can you organize molecules with different properties to create a computer chip like the current computers?
Yeah, that's a very interesting question. So now that there are good switches available, you can definitely create circuits based on and off switches. But in our current day computers, we use transistors. The molecular transistor is still very difficult to make. It can be made. Some groups are very good at it, but unfortunately, usually only one at a time. So that is one of the challenges. And of course, the way current transistors are being used, they're also being used in signal amplification. I think signal amplification has still yet to be demonstrated in a molecular transistor. So in that sense, the answer would be no. We don't really have molecular transistors that are good enough to build traditional computers with. But I think that is not the interesting thing to do, because the transistors we have in our computers, they are unbelievably good. The smallest feature sizes are already 5 nanometers, so they are already approaching the size of molecules. So it's difficult to see how molecules can bring a benefit. So I think the way to go forward is to see molecules or molecular electronics or molecular-based electronics as a complementary technology that enable things that is very difficult or perhaps even impossible to do with silicon. I think that is the way to go. Yeah.
Very nice comment. And the second question, first a comment, very interesting research, Professor. The question, is a protonation turning your nitrogen compound into an Esaki diode, or is PAPF-PPD a new mechanism for molecular diodes?
Yeah, that is a very good question. Of course, the Esaki diode is the hallmark example of devices that show NDR. But NDR in Esaki diodes is really based on and off resonant tunneling. So the conduction channel and the Fermi levels all have to line up, and you really go, and only on the resonance you have the maximum current, and when you go off resonance again, the current decreases. These molecules are fundamentally different because you go from one molecular state that has one tunneling channel to a different molecular state that has a different tunneling channel. So we change tunneling channels. So in that sense, it is fundamentally different than an Esaki diode. Well, can in principle Esaki diodes be used for neuromorphic devices? Well, the answer is yes. There are a few examples in literature where devices with NDR are used for neuromorphic computation schemes. Yeah. I hope I answered the questions that were asked correctly.
Very good. And also, if I can chime in a little bit, the Esaki diode is a reversible process, while in your case, we see hysteresis. You have an adiabatic charge tunneling process.
Yeah, by far most NDR devices don't show hysteresis. We have a large hysteretic behavior. Yeah, that is true.
Yeah, very good. Thank you very much. I think now it's time for us to take to the next step and switch to the panel discussion. And I will ask Zihong Ne and Professor Xinyu Liu and Julia Chan to join us in the panel. And then we will give our ex-challenger the first chance to ask questions.
Thank you, Martin. It's a great honor for me to learn the wonderful works of Professor Nijhuis tonight. And as a learner of this field, I have two questions with special interest for Professor Nijhuis. As you have shown in the slide, it's very fantastic that several molecules could have a similar behavior to the single unit of a traditional RAM. And my question is, like for either for a processor or for a memory, we want the functional unit to be as durable as possible. But for the organic molecules, the non-ideal charge transport of the electrons might cause heat. And would this kind of heat do damage to the molecule structures, thus affect the functional of the molecular electronics?
Yeah, that is of course a very good line of thought. So I think again, molecular devices are likely not to replace traditional devices, because traditional devices are so incredibly good to begin with. But in alternatives, think of our brains again. Even if you have a little bit of damage, or not every device is exactly the same, but molecules are naturally a little bit disordered. So there's always going to be a device-to-device variation that is likely going to be larger than the silicon-based devices that have been optimized for more than half a century, that can be produced on massive scales with incredible small variations. But our brains, they can compensate for that. So when there is a defective area or a non-functional area, it can be easily bypassed, and a different part of the network will compensate. So in that sense, bio-inspired computation are based on networks that are capable of repair, of compensation, and especially molecules. Think of the field of supramolecular chemistry. There are plenty of examples where molecular systems are capable of self-repair. There are self-repair polymers. Some materials you can cut, you put it back together, you wait a little moment, and they are strong again. Yeah, I think those kind of self-correcting and self-healing probabilities of molecular materials, yeah, it would be very fantastic, would be very interesting to exploit that in such devices. To overcome variation or maybe even some potential damage during fabrication processes. So I think that could be one way to solve these issues or to address these issues. Yeah.
Thank you very much. I think the molecular electronics are very promising for study the neuromorphic computing. So here's my second question. As for me, I think the current study of the molecular electronics is still like modeling it as simple electronic components like a diode or a resistor. But for me, I think the information transport in a real neuron is pretty complicated. I think there are plenty of acceptors or more complicated biological processing that's happening during this process. So how could the molecular electronics emphasize this kind of sophisticated processes?
Yeah, that is a very good question, and I maybe should be a little bit careful because I do not want to give away everything I'm currently writing in one of my European proposals. But it's a very good question. Of course, these junctions are very simplistic. And in a way, I find it already remarkable that these simple molecules, because compared to a biological system, the molecules I just discussed, they are very simple. Yet they can already mimic some of the basic function. So I think it is very promising. One way to move forward is maybe to move more to hybrid devices. So one of the things we are now working on in my group, and now we have, for instance, our devices are relying on protons from air. But what would be if you what would happen if you would now spin coat a very thin layer of polymer on these molecules, something like p.PSS, which is already a well-known proton source. Then already within the device, we add additional complexity because we add more molecules that are also very dynamical. p.PSS is quite a complicated polymer, in fact. Then I hope we already start to emulate more complicated function as well, and not being so sensitive for the relative humidity of the environment, for instance. So, and along these ways, there is basically nothing holding you back to make the system more complicated, and add more complexity. The other day, I saw, for instance, talks from the University of Eindhoven, where supramolecular chemists can make artificial components, artificial containers, where whole reaction networks can take place inside. So that really start to already look more complicated and complex than synapses are. So I think the chemistry is there. And now we understand the basic function of junctions. Now we understand the basic design rules of switches in junctions. I think now we are ready to add more complexity with the goal to emulate more complex neuromorphic function. Yeah.
That's a very detailed answer. Thank you very much. And a very cute puppy, by the way. With that, I would like to give the time to the panelists.
Thank you very much, Dr. Julia Chang, and for everyone. And in the panelists today, something a little bit unique is captured because although Professor George Whitesides is not here, I can almost see his representation in each and everyone who is in the panelists today. Most of us having worked with him as a postdoc, and Julia by extension, being mentored by 3 ex-Whitesides postdocs. And so I wanted to ask the panel to kind of digress a little bit for the sake of the audience and the students out there and discuss a little bit about the power of collaboration and the power of partnership. We look at the people who are sitting on this panel today, and we have all worked with each other in different capacities during our times at the Whitesides Group and after our time in the Whitesides Group. And of course, Julia being almost like an academic grandchild of Professor Whitesides, right?
Yeah.
So I wanted to ask a little bit, maybe the panel can talk for the sake of the students and the audience about the power of network and the power of collaboration and the power of embracing people from different backgrounds. Because you look at us, I'm born and raised in Africa. Chris came from Europe. Zhihong and Xinyu, you came from China, but from different parts of China. And then we go different ways, and we end up being professional, keeping up the network over 10 years, right? Maintaining that network and working together. So maybe, can I ask the panel to talk a little bit about the power of network, the importance of collaboration, and the importance of reaching out to people who are from different fields, who are from different backgrounds, and who have different expertise.
Maybe
want to jump in?
Chris can start.
Okay, I will start. Well, today I showed one area of research we are very interested in, molecular scale electronics. That is an incredibly highly interdisciplinary area of research. You need engineers, you need physicists, you need chemists, you need people who understand fabrication, you need support from theory, computational chemistry. So it is incredibly interdisciplinary. And through this research, I came in contact with beautiful people. And I collaborate so strongly, so tightly with physicists, with computational chemists alike. And that really made it possible to do all of this. What I presented today was maybe the accumulation of more than 10 years worth of research in Singapore. But of course, the Eain junction started in a group of Whitesides, so we can also add 3 years of postdoc to that. But yeah, that was not done by me alone. No, not at all. There's a long list of collaborators I have to thank, of course, for that. Yeah, so by collaborating, you really can do things that you would never be able to do alone. And once you then show that you can do those things, it will just open new doors. And with new doors, you get new possibilities, and it becomes almost like an avalanche effect. So I cannot emphasize enough how important it is to collaborate and be grateful for your collaborations. Yeah. And through that, you build up a network, and that network obviously is very important. Otherwise, we would not be sitting here today. Yeah.
Yep.
Yeah.
Anybody else?
Maybe I can add a few words. I still can remember that very dynamic environment in George's group, and also the posters from a very different background in the group. For example, we have people completely from the physical department working on, for example, supercooling and working on flames and organic synthesis, electronics, and microfabrication, and so on. That's why you can see that lots of amazing things keeping generated from George's group. And after I established my own group in Maryland and recently in Fudan University, I'm sort of taking the same approach. And in my group, I also recruit students and posters from very different backgrounds. For example, I have students working on from physical department working on modeling of plasmonics, and how people working on nanofabrication and the synthesis of nanoparticles and polymer physics, polymer synthesis, and so on. And that's why, and recently we also tried to reach out some new area, and very different from my previous research in Maryland and the Joyce Group. And we recently started working on metamaterials based on three-dimensional organized nanostructures. I feel that without all these very rich background of these postdocs and students, it is almost impossible to do that. And also, we are also collaborating with many groups, for example, physical departments and many other colleagues as well.
Okay, so I think I feel very similar to Zhihong, but probably I'm from a quite different background from the rest of the folks on the panel, because I'm from the engineering side. So actually, I joined Dr. Weiss's group. I mean, it really is crossing from engineering to science. So actually, it's eye-opening when I get there. I think that, as Zhihong mentioned, it's not only a single chemistry group, right? So we have so many different talented people. I mean, working on different areas. It's really a learning process for me, especially during my 2 years in the WSS group. I think I learned a lot from, on the scientific aspects and expertise. But I think more importantly is it really gave me this postdoc training gave me a stronger spirit of exploring into different areas. I think that's really really helpful for my own independent group, because I think we are actually, I had this experience already during the PhD, but more or less our collaborations are among the engineering areas. And when I went to George's group, I talked to different people like Martin, Zhihong, and Chris. I think it's really kind of further training for me to explore beyond the engineering area. That's why when I started my own group, we continue what I have done in George's group, but we also explore into different areas. I think that's really that spirit of multidisciplinary research. That's really something enabler, at least for my group, to have new results and to explore, to have new grants and new publications. And also, I think the diversity, like people from different backgrounds, different academic background, and also different culture background, I think that's also very important, because that kind of gave us opinions or approaches from different angles. That's why I think this is really beneficial for having a nice dynamic group, and also to have a lot of new approaches or new ideas coming up to explore. I think that's why diversity is really important. And also, of course, networking. I think I still remember the first time Martin and I started a new product, and also still remember the first time I talked to Zhihong about this a glucose meter, using it to have to do paper-based electrochemical detections. I think those moments is really something like cherishable for me, and definitely, and hopefully we will have more things coming out. And now we are in different countries, and in the future, I think our network will grow, and hopefully new ideas, new products will come up. That's something I have, and is really a nice moment. I would like also to thank Alliance, because this really brings us to have a small reunion, and hopefully in the future we have some other like bigger events to attend. Have this. All right, thanks.
All right, and then last but not least, we have one question from a very special guest. When we talk about network, I'll let the guests introduce themselves. Please go ahead. And you can introduce yourself and ask the question.
Hello, everyone. I'm Yuan Li. I'm Chris' PhD student. So he actually gave there's one slide to introduce my work. Yeah, I'm Chris. Okay, so, you thanks to give us very insightful talks. I'm Chris' student, but I'm also George's postdoc. So I'm also part of YSS families. so yeah, I'm all agree with all you guys saying. So YSS group is so diversity, and I learn a lot there. Especially I learned a lot from George himself. He's the most hardworking guy I have ever seen, and almost clever guy also. That's why he got like so many publications, I think.
Hey, be careful what you say.
Yeah. Okay, so anyway, yeah, I was very honored invited by the organizer, so to come, so very pleased to able to talk to you a bit, and also join a little bit, and yeah, as a surprise to you, Chris. So yeah, and also thanks a lot, Chris, that you bring me into this this scientific world, and I really find myself really enjoy the research working, and also I now I'm doing teaching. I also very enjoy teaching, although it's physical chemistry, very difficult to prepare. But I'm very enjoyed the life I have now. Thanks, Chris. It's all from you. Yeah.
No, you did it yourself. You really deserved it. No, thank you a lot. It was really great. Yeah, to have you and to be part of that important piece of your life where you could do your PhD with me. That was really a very nice moment, and it is great to see yeah, that you are now setting up your own group completely independently. And I'm really looking forward when it is possible to travel again and to visit you at Tsinghua University. I'm really looking forward to see what you're going to do with your group, and of course about yeah, and to read all those fantastic publications that will come out of your group. Huh?
Yeah. Sure, I will make that happen for sure. Yeah.
So I want to thank everyone, and I think for the audience and those, especially the rising stars, the students and the postdocs. I think the take-home message is the science. The science is beautiful. Be bold, be daring. Venture into the world where you can actually bring your expertise into fields that maybe they look very futuristic and very far away, and you'll have impact to the world. But more important, value the people that you're with. Network with people, reach out to people, and realize that you get more done when you're a network rather than by yourself. And with that, I want to thank everyone. I think because of time, we need to stop. And I hope that everybody enjoyed the talk, and it's fantastic to see you all. Thank you.
Thanks. It's so nice to see you all.
Yeah.
So,
thanks.
Chris,
Thanks.
if this was live, I think Aris and I would have walked on stage and given you the certificate, but now we're going to have to acknowledge you virtually. Please accept it as it is. And then for the next week, we're going to have Professor Zhuangkai Wang from the City University of New York, and the panelists will be Lanfu, assisted by an ex-challenger, Eain, and we'll be talking about surprises on surfaces, so please join us. And then with that, I want to say thank you very much, and thank you for the wonderful talk.